Hello, everyone. It's so nice to have you back on our podcast. Today, we're going to really dive into what AI operations is all about. How do you get started with a project in your company? Today, we have a really special guest with us. Anatoly Melamud has done just that. He's an AI architect that designed a transportation and logistics AI system. And he's had a lot of learnings as a result of that. We want to share those learnings with you today so you can do something similar or not make the same mistakes along the way. So, Anatolia, how are you today?
Thank you, Vicky, for the introduction. So looking forward to conversation, which pretty much excites everybody. I know creates a lot of hype and interest from the larger communities.
One of the challenges I think out there is really around data because machine learning is based on data. How do we actually make sure that the data we're using for these models is clean? How do we go through the process of identifying the data that we actually need?
Yeah. Thank you, Vicky. Excellent question. Yes, data is the beginning of this AI journey. So every time you think AI, first you think about the data. The data could come from different sources and different formats, like structured, not structured data, georeference data. So it's a lot of different sources may contribute to the AI implementation. So it's a lot of issues around that.
You talk a lot about data you can trust. So, how do you identify? What does trust mean when it comes to data?
Trust means many times different things to different people. Of course, you want to have a valid test, right? So you start with the test. How are you going to test the data run by different people, get some kind of consensus on what the test is going to be. You involve as many people as you can from business engineering community, from your customers, and kind of show them this is how I'm going to test. And communication is the key here. So nothing can validate the data, but the good, very well developed, defined test. So the testing suite should come first, and definition of the trust should come from the test. So if you accomplish that and the trust is established through the quality testing of what you're trying to understand, then you can go basically and apply the test to your data. And the test will basically make consideration whether you passed or failed the test. Look at all the data sources, test at the front where the data is coming from the source. Because later in your process, after machine learning algorithm or any AI algorithm start processing that, it's very hard to extract the data, understand the derivation of that, because some of this like black box. So you establish trust at the source when data is not being massaged or not being changed. So you establish all your check and balances and testing there. Establishing quality at the source of the data, that's extremely important. So that's one of the rules we establish when we start building the system. Don't try to catch it later as part of your established machine learning algorithm. It's impossible because, again, it's a black box and learning process in general. So people talking about explainability of AI, explainability of machine learning algorithms, but when they talk about explainability, it's pretty much the missing, I think, the point that machine learning actually impacted by the source of the data. So it's too late to try to worry about explainability of fixing after machine learning algorithm establish some kind of regression or classification. So the lesson learned is basically establish your quality checks at the source.
Clean your data, make sure you have the right testing in place. Don't try to do it later on because then it's much harder to figure out which is good data, which is bad data. So spending time up front, gather requirements is really critical. What's about another thing that you maybe learned now that your system is in operations and running with the customers? What are some of the things that you're learning as a result of that deployment?
Then after you basically establish the kind of trust at the source through the testing, you're moving to the next step, which is like how your algorithm, machine learning algorithm is going to learn. How much data is enough for it to learn, right? So people saying the more data you basically fit into your system, the better is the quality of your solution, which is not always the case because it's more about understanding how basically your data relate to each other. So this is mathematical foundation, data being correlated. So if you fit correlated data, like highly from different sources, they mean same thing. They create bias of a large sampling issue versus like smaller. Sometimes very small subset of data becoming more important for the process of learning, developing quality solution than the larger scale volume. We should understand how you calibrate your data, right, between different sources. So in other words, how you basically provide samples which could reflect the reality of the system you fit into your algorithm. So
And I
then
think you've got a really great example of that around the systems. For example, as trains running in Tallahassee, Florida have a different schedule than maybe ones running in California. They have different geography around them and logistics around how they transfer from A to B. So by combining both of those places into one model, to your point, actually gave you more inaccurate results than really creating small, more localized contextual models that gave you specific results for the area that you were dealing with.
Okay, that's a great point. If you look into large transportation system, what happened in North America, our company serves the entire North American operations. The scale is enormous. You have transportation events in Alaska and Florida, in remote areas, in areas where you have high density population and metropolitan areas. So it's completely different patterns there. So if you mix that, it's important to understand that metropolitan and remote areas, the data coming from more remote data where the transportation event not as frequent as a metropolitan area like Chicago or Atlanta, New York City, Los Angeles. So that's extremely important. That's where we've tried different models and eventually arrive at the point where localized models means the smaller kind of more homogeneous type of system we apply algorithms to or develop regression models and classification models against the better the quality in general. In other words, every time you run no classification model, they can produce different results. Sometimes this area is included, to other times you run, it's not. This is by nature of, I can talk a lot about the classification models. So classification is not as deterministic as some people think in general by nature of the algorithms. So this is why different type of set of studies are required to define your localization.
So you're constantly tuning the models to make sure it's still producing the results that you need, that you're considering that the data is not off, right? Because you could receive data that you didn't plan for example, and then you have to figure out how to fit it back into what you've created.
So you're really looking at the opportunities, how statistically you can randomize your data to come up with the right set of localized models.
Let's talk a little bit about operations, infrastructure. You know, we know that running these models is very expensive in terms of power and potentially using cloud providers and scaling with them. What are some of the lessons you've learned from cost versus benefit and how you scaled your model?
First, come up with different ideas of how you do the composition of your models, right? So you have to, before you even scale, you think about statistical properties of your data set, right? So time series data has certain statistical properties which impact how you build a model. You're really looking at how you can come up with a more or less stationary data for you to improve quality of your prediction. I have to create, let's say, 2 million models because scalability is very expensive. Running small models versus large one extremely expensive. So before I go and give you business estimates how expensive it's going to be,
Right.
you have to prove to them, mathematically speaking, your foundation of your model lead you to this solution to improve the quality. Now going back to architecture in the cloud in particular, so of course machine learning operations developed more around K-Surf and other models developed by different companies. They basically built around deploying one model at the time. So you deploy it as an encrypted model. So it's like a piece of software you deploy and piece of software generated by a machine learning algorithm. So those machine learning algorithm learns and then you generate code from the machine learning algorithm. It's not human built code. It's very important to understand. It's a black box code generated by the system automatically. Architecture of our system, we're deploying cloud and we're deploying Kubernetes. It's a KS, it's Kubernetes service. Microservices architecture. So now basically you have a lot of these paths. You have to deploy millions of microservices, which basically serve your model. You have kind of two at the same time. You create so-called redundancy, which
Yeah.
allows you to have 24 by 7 operation. And this
Right.
redundancy, of course, brings 3 times as many resources, capacity requirements to your business. It's becoming extremely expensive to deploy. So that's where we build a framework which allows us to scale.
You take us through your thought process. You had to figure all this out from scratch, the high availability, how do you scale? What are some of the questions as others listening to this and they're trying to build these models? What are some of the questions or best practices they should be thinking about in terms of deploying these models?
You need to think about how these models are going to be used. How many of them you're going to be used concurrently. So your main goal is basically looking at the peaks, right? And working through the peaks. So if you can handle your peaks, you
Right.
can basically handle everything else. But then what's happening with this is that it means you can basically study the peaks, but you may not always predict where exactly it's going to happen. So you let system figure out how many hardware pieces it needs. So you implement auto-scaling solution. The challenge with auto-scaling, it sounds great, but challenge with auto-scaling is good for stateless paths, stateless microservices. Every time you deal with the stateful microservices, so basically scaling up and down is basically losing your data state, right? So that's where you have to come up with the solutions where your stateful services, which has to be maintained, right? But still keeps your computing resource occupied because you cannot just let it go from the system, right? So that's where the challenges are, how you manage your state with the caching type of solution. And at the same time, or just save it to a database and recover from database and how expensive it's going to be and what's going to be impact on performance. So range of different solutions is different from like stateless service and stateful services because stateful services represent the biggest challenge for auto scaling. So your data, your mathematical properties of your data, your quality lead you to ability requirements, high availability requirements, how you manage stateful services. This is where you come up with the architecture, which can be based on the trade-offs deployed in cloud